Oh, just okay. Yeah. So basically, chapters 5 and 6 are deal with electricity and magnetism. The chapter 5 deals with the static, what we call static fields, and I'll describe that in a minute. And chapter 6 deals with moving fields, and moving electromagnetic fields are basically light waves. So we'll discuss the difference in those and get through both of those chapters today. Let me get my key up and running here. This is an interesting topic. Again, it's something that you have an intuition for because you deal with electromagnetic waves are very much more part of your life, everyday life, than they were mine. Uh, Back in my day, remotes, when I was a freshman in college back in 1982, you can believe it or not everyone had a remote. That was something that was being newly introduced uh, in the society as a common thing. And it was really only with televisions. There was no such thing as a key fob back then. Uh, so the idea of dealing with electromagnetic waves and certainly not anything like having a camera on your phone and being able to communicate with anyone halfway around the world and teaching a class. Now they existed, but they were, part of military programs. I mean, the public, I didn't know, we didn't know anything about that you could do that already. Um, so it wasn't a part of popular culture uh, and a part of our natural mindset of possibilities, of practical possibilities of things. Um, but now, we it is, even elementary school kids have a practical understanding of what an electromagnetic wave is. One of the things that I used to teach, or I've been teaching almost 30 years now, and people used to have there used to be this kind of stigma, maybe not so much at this level, conceptual physics, but with the more mathematically oriented physics courses like calculus based. There was this kind of dread that electromagnetism was much more difficult than mechanics. And it wasn't really true, but it was just a perception. And the reason that was is because with mechanics, these are concepts that we kind of have an intuition for starting as a young child. I think I mentioned this maybe on the first week, but I'll say it again. I used to spend a lot more time talking about this as an introduction, but I'll just mention it now. Because you run around, you fall down as a kid, you hit the ground, you know what an impulse force is, you have a sensibility of what force is. You also have a sensibility of the concepts of speed and acceleration. Acceleration is what you feel when you're in a roller coaster. Negative G's are the butterflies you feel when you're in a roller coaster and you're going down. Positive G's are the thing you feel, when you they have some of these fast roller coasters like over at Universal City. They take off really fast, or an airplane, and you could feel the compression back against the back of the seat, or or even when you go around a curve and you kind of pressed up against the core. Well, that's centripetal force, but it's also kind of a positive uh, G force if you're going fast enough. But also at the bottom of the roller coaster, at the bottom of the hill, when you feel the compression, and then you kind of swing up and you start to right as you start to go up. That's a positive positive G force. So when you start to talk about these things within the context of the physics and the concepts and equations, it feels like it's easier because you have a sensibility of what they're talking about. But with uh, electromagnetism, oftentimes that's not the case because you we can't visualize, things like fields and charge and stuff like that. You don't. it's not as much of a sensibility at what it used to be not be, as a kid coming up because you didn't have anything where you practically thought about or used them or had an idea of what their properties were based on experience with utilizing these concepts or experiencing them. But that's not true anymore because any of these devices from cell phones, kids, even babies watch them on, you see them in the airplane and they'll put on some kid show on the cell phone and the kids watching it the whole time. And so even as a small child, you begin to develop a sensibility of the idea of a field or a way, where is this of a signal? You go into a concrete building and the signal maybe not might have some static. Uh, and you can't see the television show as well. And you have a sensibility that something associated with the building keeps something that you're connecting with, makes it more difficult. Ideas of satellites, you see every neighborhood now has the cell phone towers and kids can, the child, you're going to grow up asking what that is. And so anyway, that actually helps your sensibility to at least begin to imagine that there are these things out there that are called fields and you can't see them but they're really powerful because they can affect our lives in a positive way and they have become part of our practical experience. So visualizing, I believe, is half the game. It depends on your learning style, but I think I've mentioned before that I'm a visual learner. So having an idea of what a charge is doing as it moves around within a conductor or a non-conductor. Conductor is a metal. A non-conductor is something like plastic that can't conduct electricity. Um, Understanding what a charge, what it has to do, what its relationship is with an electric or magnetic field, uh, it helps to be able to visualize. So working with these kinds of tools, phones and things like that, key fobs for televisions or the lock to your car. These things are very especially with electrical appliances. And if you are trying to become an electrician, electricity does affect our daily life. Yeah, absolutely. That's right. That's right. So, good. Well, what do we want to start with here? What did they start with? Oh, they start with forces. Science in the making, forces. Yeah, electrical field. Okay, let's do that. Well, will remind you. I think we had a conversation on the first day or so, but this is a nice time to have it. At some point, we did about fundamental forces in nature. I believe I mentioned that there are four, and that we would be talking about the first two within the first part of the course, and maybe near the end of the course, mention the second. Look and delve into the second two a little bit more. But can anyone name the four fundamental forces? These are the forces that we think were beginning around near the beginning of the Big Bang. That's still the standard model is a thing that is a name that is used to describe in cosmology how we think the universe was created, and it has a name. Gravitation is one of them. That's right, Julia. It's called the Standard Model, and it incorporates a lot of things uh, associated with matter and cosmology and how we think the universe is put together. But part of that Standard Model, one of the big things that everybody's probably heard about is the proverbial Big Bang, that we think somehow the universe was this small singularity, and a singularity is just a small point. It's a point that's infinitesimally small and has no shape or size. if you can imagine the whole universe that we can't even see how big it is yet. We can only see certain uh, distances. I remember what that is based on the telescopes we have. And the universe is expanding. And, the whole idea of things you've heard, we think it's going to contract. Some people think it won't, whatever. We'll get to some of that later on. But all of that, everything you can possibly imagine and see when you look up at the sky at night, you know, was this smaller than the point of a pin on a head. And it had all that energy and stuff in it. And for some reason, we don't know why. Well, conventional science doesn't say why or speculate why it burst apart and just began to spread. So shortly thereafter, when I say shortly, I'm talking about, you know, and I don't have the time periods, but certain things were formed and happened in milliseconds from the Big Bang. So you're talking at very short time, we begin to see these fundamental forces. Um, and you got it there. So Tamika, it's gravity, electromagnetism, strong nuclear. Oh, awesome. That's it. Yeah. I don't know if we mentioned it or not, but if we didn't or if we did, good that you remember. Yeah. So those are the four. At one point, we thought there were five. We thought electricity and magnetism were two different types of forces, but those were combined in the 18th century, in the middle of 1800s, into electromagnetic force. And I think we actually have combined technically electromagnetic strong and weak. But the one that's seemingly was the easiest, gravity is still the holdout. We haven't combined gravity, everything. But I think Einstein was one of the first persons to pose the idea that all these forces were part of more universal force called the theory of everything is kind of the general term for it. But grand unification is what the original name was, grand unification of forces. That all these forces come from are there's different aspects of a much larger force, which is a fundament, the ultimate fundamental force, the God force, just like they looked for the God particle a few years ago, which was the Higgs boson. We think that there is this force that's a combination of all four, which goes by several names, officially grand unification or the theory of everything, but the God force, this combination of all these four. So gravity is the only one that's not there yet. So anyway, so we'll write them down. Uh, Fundamental forces. They are gravity, electromagnetic, weak nuclear, and strong nuclear. And if we were to put them in a hierarchy, actually, this is the hierarchy from weak to strong. Gravity is actually the weakest force, which is really counterintuitive and really ironic, I think. When you look out in the universe, it looks like gravity is the thing that's controlling everything. But in fact, it's much smaller than the electromagnetic force. And we'll compare that in a certain way, or at least electrostatic. And the weak is the thing that keeps electrons close from falling into the nucleus, and the strong force is sorry, the yeah, what did I just say? Yeah. So the weak force keeps the electrons from collapsing in to the nucleus, and the strong force keeps the nucleus from bursting out because they all have the same charge, protons in the nucleus. And we looked at the simple Bohr model of the atom where all the protons are in the center. So let's talk about what I mean by that a little bit as we move forward. So going to say something else here. Forces, yeah. Oh, grand unification or the theory of everything is grand unification is the idea that all fundamental forces should be combined, are combined into one universal force or God force. and unification of forces. Um, or stem from one um, universal force. In parentheses, God force. Because it's interesting that from mechanics and calculus, what we learned is that if you know the force on an object because of Newton's second law, force equals mass times acceleration, you should be able to then figure out something called an equation of motion using calculus. That is, what is the equation that defines the motion of that object? And so in this case, it would be the motion of the universe. If we had the force, we could put that force into Newton's second law, work through some calculus, maybe a bunch of it, and basically figure out, the equation or set of equations that define how the universe expanded. Um, well, that we haven't done that yet, and that's why they call it the theory of everything, because it would be the one force that would define how the universe, expand, and should be able to then know what it's gonna do, whether it's gonna just keep expanding and peter out and die cold, or if it's gonna somehow come back in, if it's oscillatory in nature, and all of that would be evident from the equation of motion, the dynamical equation of motion of the force. Dynamic meaning the equation associated with forces, and the kinematic equations. Out of that, we could get equations of motion, like how fast it's, like in time, what it's doing. So that's one of the reasons that it's so significant of any system. If you can evaluate and know all the forces, that is the functional form of all the forces on a system, then you should be able to analyze that system for its motion. So that's one of the things that is so significant about trying to figure out the unification, of all forces. But yeah, yeah. So it's a big deal, and it's clearly a difficult problem because Einstein in fact, I think it was actually proposed. If I don't know my history right, it might have been proposed before Einstein came in the picture. Uh, maybe not. I don't. Yeah, maybe not. I don't know. But we've been looking for that for a long, and this is part of the one reason why people are looking for things like dark matter and dark energy, which are two separate things, because we think that might be associated with, well, any information that we get will help to move us in this direction is going to help. But anyway, there's a lot of problems in physics, certainly along at the level of cosmology, that hinder us from being able to understand uh, the unification of forces. So, yeah, yeah, yeah. Okay, so the first thing I want to do is, I think they at some point get to this, is I want to justify the point that I just made here, that there's a hierarchy, that uh, gravity is the weakest force and it's weaker than the electromagnetic force. Now, one caveat I'll say about this is electromagnetic, again, that's really next chapter. This chapter, we deal with looking at electricity and magnetism essentially the way that we dealt with it before we understood that they could be combined. They come from well, they are separate forces. Electricity is a force, magnetism is a force. And we we understand that they are related, And I guess it goes through and talks about the electric field. It gives talks about the magnetic field of the Earth. Let's first talk about an electric field, then I'll talk about a magnetic field, and we'll quickly put them together, show what the relationship is. Guess we can do that. Now here, gravity, they just write down the equations for you. Yeah. Let's talk about gravity and well, we're going to break down the electromagnetic force into two parts, electric and so static. I'm using these words, electrostatic and magnetostatic. Um, I'll just quickly ask you a question and then give you the answer if you don't know, so that I can understand why we need to break them apart. Does anyone know how? I think I asked you the other day how uh, current is created. I think I did. Maybe I didn't. I don't know. It might be confusing classes. But let me ask you this right now. Does anyone know how can anyone describe, just from your own sensibility, what a electromagnetic wave is and how it's created? Does anyone know? Do you know what I mean when I say wave, what I'm referring to? Vibration. Good, Julia. Can you give me an example of a wave? Something where you've seen it in nature, or it is associated with vibration, but it's not just vibration, right? Because um, you could have well, just now my air conditioner came on. I don't know if you heard it, and it's on the wall of my windows. If I were to measure, like have some sort of sensitive device on the window, you could see that the windows will shake because of the motor of the air conditioner. Now that shaking doesn't necessarily, well, it's not friction. No, it's not from friction. It's just like, well, like if maybe you're sitting at your desk right now and a large truck rolls down your street. Maybe it's a bumpy street. It doesn't have a bunch of potholes and things. When it does that, it could make your windows rattle, right? So the rattling of the windows, that's something that's really considered vibration, but not necessarily a wave. It doesn't necessarily have anything to do with friction. It could, I guess, but not in this case. It doesn't. In a simplest case where there's no, yeah, But so how does another example, I guess, of oscillatory motion that not necessarily mean there's a wave involved is like a pendulum, right? In my room, let me get some practical things here. I've got uh, an extension cord here. I can kind of treat this extension cord like a little pendulum, right? If I touch it like the hand of a grandfather clock, that's oscillation. It's associated with vibration. We call it oscillation when it's not something shaking really fast. But that's that's vibrational oscillatory motion, but it's not necessarily associated with a wave. Now, all waves are associated with vibration, but not all vibration are associated with waves. That's the point I'm trying to make. So, and actually, those were three examples of vibration: shaking glass, vibrating pendulum, whether it be something you can create, like you on a swing, on a swing, or a grandfather hand of a grandfather clock. That's all vibration or oscillation. Kind of using those words interchangeably. I guess I would make the distinction is that oscillation is something where the period is not that fast. Like, for example, the another example of oscillation would be if I can turn the camera around here. Oh no, sorry, close. Oh, yeah, here we go. Another example of oscillation would be, can you see my roof over there with the um the spinning what do you call that? Ceiling fan? Those we kind of refer to those things as oscillation. But vibration, it's related, but it would be more something like the shaking window. I mean, you could yeah, that's, they're basically the same thing. It's just kind of like we refer to in kind of everyday terminology, something that shakes is usually something that's happening really, the oscillations are really fast. It's maybe like a small, something that rotates or oscillates, would be something that's spinning, for example, or a pendulum that's part of a circle, but it doesn't have a full circle, but it's going back and forth. So that's how I distinguish between shaking or vibration. Shaking and vibration are definitely synonymous. Uh, those two words and rotation, not necessarily. Anyway, none of that has to be associated with it. It can be, but it doesn't have to be. So, one more try then. Can you give me an example of something that actually does wave and is slightly different than that kind of motion that I just described? Any kind of wave is one. Yeah, so give me an example. Well, let me give you a hint. What if if everybody got out of their house right now and walked due west, what would we where would we end up? At the ocean. Yeah, and so ocean waves. We see the beautiful ocean waves lapping against the shore all the time. That's a wave. Another way I could, if I won't do it, but that extension cord is plugged into the wall. If I kind of came out and made it somewhat taut, like walked a few distance away and started vibrating it, shaking it, what would you see moving down the length of the extension cord? You kind of whip it, right? And you can see like either a pulse going down or you keep whipping it and have ripples going down. Very much like that of the waves of the ocean. So those are called mechanical waves. And they are waves because the difference is there's translational motion involved. It's not just, there is oscillation, right? If I were to put like a dot, um, and again, I don't have, I never really had a good way of illustrating. I had these little strings that sometimes would try to do that, but they're not heavy enough. But you know what I'm saying? Like if I took a long string, like for example, was that exercise that's actually a very good one. What's the exercise that the body people do in the gym now, where you have these two large ropes and you connect them to something, at a pole or something, and then you do that thing, right? You can see the waves going down. Maybe I could pull it up on the internet. On the internet, that'd be a good thing to illustrate right now. Because I want a good example I'm going to make here. Does anyone know what the name of that exercise is? I don't know what it is. I have to. Let's see here. We could. Um, actually, maybe fine. So workout people here. I don't know what that's called. Battle roping. Okay. Battle rope workout. Okay, let's see this guy here. Somebody doing a battle rope. There you go. All right, now let's look at this. Let's look at this while I'm talking. Now you can clearly see that there's this pulse or pulses uh kind of above and below. Like if you had it straight, there's this kind of wave that's moving and it oscillates above and below some horizontal. Like if he just held his hands like that, held it straight out, there would be some average position of the rope, but then the disturbance, the pulse, there's one above that average position and one below that average position. It looks like a wave. Put them together, it looks like a wave rolling down. Now, you see that there are marks on the rope. There's writing. Now he's doing something else, I guess, a different one. But let's see. Let me go back to the other thing first. If you imagine a spot on the rope, okay, he's doing all kinds of things. So I'm just let him go here. Maybe go back to the first one. That guy. If you imagine that you put like a white spot, like painted a spot on the rope, what you would see in this particular kind of wave is that that spot would just be oscillating up and down, straight up and down in an ideal case, right? Let's come back to class so you can see me. So like, let's just do my hand like this, right? So again, this is what I was saying, like if I held my hand straight, first of all, my arm is going to be the medium of the wave. Now, this is kind of an average horizontal position. As the wave goes down, it makes like disturbances above that average position and below that average, kind of like in a what we call a sinusoidal kind of pattern. I can draw that on the board quick. So this is the average position. Then when you start to kind of wave it, it kind of does something like this, right above and below that. And it looks like that wave travels down a particular direction along the line. But if I were to look at just one spot on the on the rope isn't actually traveling. And I can prove that by looking at one spot on the rope. That spot just goes up and down. So any spot on the rope actually is oscillating, right? It's just an oscillation. So that takes me back to what I think it was you, Julia, who talked about oscillation, battle ropes, exercise called that. Yeah. So oscillation is definitely associated with a wave, but as I just previously showed you, you can have something oscillating or rotating, and it's not associated with a wave. Right. So this point, any point on the rope is oscillating at a particular period as the wave travels down the medium of the rope. And what do I mean by medium? Well, mechanical waves, this is the teaching that we teach now, and I have a slightly different problem with that, which I'll talk about in a minute. But mechanical waves are waves that travel on some sort of physical medium. So in the case of the ocean, the water is the medium. So it's considered a mechanical wave. Ocean wave is the medium is the water. In this example I'm giving here with the battle ropes, the medium is the rope. Is the physical is the physical rope itself. I just put that again. There's another kind of wave that I'm actually using here as I talk to you. It's called a sound wave. A sound wave, well, actually, that's not considered a mechanical wave because even though it is traveling on the medium is the atmosphere. The atmosphere, it's not really, we designate it as sound wave. A sound wave is a separate category of wave itself. So we don't really call it mechanical, even though I guess you can make an argument that, the atmosphere, or it doesn't even have to be an atmosphere. It could be mechanical. I can make sound wave travel through wood, right? If you just hit it, or in water. That's why sound is much more amplified in water, because in that case, the sound wave is traveling on the water itself. So clear, otherwise you wouldn't be able to hear anything underwater if it just so if water itself is a mechanical wave, then technically I kind of think of sound as a mechanical wave. However, as a category, we put that in a separate category, even though it is because of other properties that are slightly different associated with a sound wave. But it certainly is mechanical in nature, I would say, make the argument. So let me ask you this. If the actual particle or parts, the physical part of the medium is the thing that's oscillating, what in the case of a wave on a string or in battle ropes, what is it that is traveling down the wave, down the string? What is so the rope we say is waving. That's the thing that's actually oscillating, and you can tell that by any, as I've said 3 or 4 times now, any particular part of the string that's oscillating up and down. But what is it that is translating down the wave, down the rope? What? Let's make that a question. In the case of battle ropes, what seems to be traveling down the length of the rope along the wave? Along the or in the wave. Like we can, what I mean by traveling in the wave. If I were a surfer, right, and I was, caught a wave, I'm translating, right? I've caught one of the kind of like I'd be on one of these humps here, traveling down the hump as the hump moved down. Now the hump isn't actually translating. Why? Because the hump is actually, as we call it, a crest and trough of a wave. The crest here is not actually, it's not actually moving, because that would mean that that part of the string, the whole, if the rope were actually translating, that means as the guy waved his arms, the rope would leave his hand and just start moving down the gym somewhere. I don't know, so clearly the rope is not actually translating meaning moving with a horizontal speed. Neither of these particles, they're moving vertically. So, but clearly you could have something like, if it were ideally, like if you compared it to the wave at an ocean, something is moving because it has the same shape as someone catching a wave and and riding the crest of a wave in a horizontal fashion. So my question to you is, and actually it'd be the same question for the water wave as well, because the water technically, now there's a little bit of, it's not an ideal case because we definitely seems like the water kind of moves back and forth along the shore when it kind of gets to the shore. But the whole ocean, it's not a tsunami. In fact, a tsunami doesn't really even wave in that same fashion and it definitely translates. So when we have just the regular waves at the ocean, the water of the ocean isn't translating. So it's basically the same thing, even though we have some little losses there because of what happens, as the water hits the shore. Uh, so for the most part, though, I could ask the same question. What actually, along the mechanical wave of the wave at an ocean or the wave on a string, what is it that is translating down the length of that medium as the wave uh, travels along? Give you a hint. It's actually something we've discussed in this class in previous chapters. Genevieve, are you there? Want to give it a try? Soleil? I'll give you a big hint. I've said previously that this thing, it acts like a ghost, has the same behavior that we would kind of attribute to ghosts in like scary movies or things. What is that? And then we said a lot of other things about this quantity, but that's one of the things, first things I said about it, is to kind of give you some sensibility about it. Well, look at Tamika. Tamiko? Awesome. Good, Julia. Yeah, it's energy. Energy is the thing that translates on a wave. Awesome. Good. Very good. I feel like I'm making and doing something. So yeah, energy is the thing that travels down I think it's the question mark. And that's any wave. Energy is the quantity that travels down the length of a mechanical wave. Travels. I'd say any wave. It's not just a mechanical wave. But these are examples of mechanical waves. And where is that energy coming from? That oscillatory energy? Well, clearly the guy, it's coming from the guy, right? It's his mechanical, he's creating a difference in potential and kinetic. He has certainly potential and kinetic energy in his hands as they move. Where does that energy come from? It comes from the metabolism of the food that he has in his body. Where does that energy come from? It came from, the sun or whatever was causing the plants or the meat to grow that was in the food. Where does that come from? Well, it comes from the sun. Just so again, that just goes back to this idea, this universal idea of conservation of energy. That once going back to that Big Bang, once that thing blew up, whatever energy it had compressed in it, that is the energy contained in our universe, and it's not created or destroyed. It just changes forms all different ways, and that's everything you see. We can apply conservation of energy, not just the conservation of mechanical energy as we do for very specific cases in this class, but just the conservation of energy in general. And even we did with thermodynamics. The first law of thermodynamics is a statement of conservation of energy. As I said, when you have things, temperature changing and things coming to equilibrium, all of that is just part of the universal law of conservation of energy. But yeah, we have energy moving down the wave. That's what a wave is. That's one way to think about it. Any wave you see anywhere, any kind of wave, where there's electromagnetic, well, the other one I was going to say was sound. Well, I did say that sound is a certain. Oh, we'll talk about how that happened. I think there's a chapter devoted to that. We'll wait to that. But that's also again energy, just traveling along the medium of a fluid or a solid, like a wall or a glass or the atmosphere. All right, good. Yeah, energy travels out the wave. Now, um, again, I know my lecture might seem a little bit disjointed because I want to compare these two forces. But what happens is, I don't like to use any word at any time that I haven't defined. So what happens is in the process of discussing things, you have to use words, maybe you've heard them before, but we need to establish them as a definition before we use them. Otherwise, it's just you're putting confusion on confusion. So that's why I kind of seem to have these tangents and things. Um, because I can tell when we're using a word for the first time, even if it's something familiar with you. A lot of times we have erroneous perceptions or preconceived notions about certain quantities. But because we're in a physics class now, we need to clean that up a little bit and actually talk about what's the appropriate physical, or at least the conventional or traditional conventional um, understanding of these words, because sometimes they can be slightly different than how we use them in our everyday lexicon, popular culture. So that's why it seems a little bit disjointed. I hope that's not too confusing. Also, with the idea of waves, it's going to be in the next chapter. We'll revisit this idea and talk about. You might have, if you had any kind of earth science course or anything, you probably understand the concept of a wavelength and a trough and a crest associated with a mechanical wave. But we'll put this picture up again, and we can go in and quantify it a little bit. For now, I just wanted to kind of give you a qualitative introduction of how we present these things, if you haven't seen that before. And this represents the speed of the wave here. This little arrow here is a vector that represents means the wave is moving from, well, looking at the board, it would be from left to right, down the medium of this rope. wave. So I hope that's a little bit clear. All right. Any questions? Because the next thing we're going to get to right now is going to be really interesting. I find it pretty fascinating. Now, I'm not going to well, yes, I will. I'll give you a little bit of history about what we're about to say. So in this couple pages in, they have some equations there that they're working out, 2 or 3 pages in. They get to something called Coulomb's law there. And I guess I don't know if they had introduced it before. I don't know if this is the first time they've introduced this other equation. They don't actually write it down. They do write it down, but they don't. Yeah, maybe they did introduce it back somewhere. I think they would have. I don't think I did it in class, or maybe I don't know. But anyway, uh, we know what now. Oh yeah, I was going to break down electromagnetic. Yeah, we haven't done that yet. So, and I asked you how a wave is generated. That's where I start. So let's go back to that. How an electromagnetic wave is generated. So I've shown you how mechanical waves can be generated. How are like what is the idea of a field, and what like there's a couple things we got to clear up there a little bit, which I'll do right now. What time is it? Okay, 9:02. Well, there's some, that we have a gravitational field. I like to make an analogy. I told you that there is, well, the first day, I think I told you that I have 4 themes that I revisit as part of my overall teaching philosophy in physics. Those themes are, not no particular order: specificity, symmetry, um, wow, I don't know why I'm getting older or something. I hope I wrote these down. Does anyone remember? Because I don't remember right now what my themes are. I don't know. I'm just drawing a mental blank. Um, that's embarrassing. It must be too important. Hmm. Um, wow. Weird. Wow. What is wrong with me today? Well, the one I want to talk about now is symmetry. I guess the other two will come. I'm not sure why I'm drawing a blank. Maybe I didn't eat my Wheaties this morning. Maybe that's why. And I think I know I've talked about this before in class because I remember telling you that symmetry didn't necessarily mean geometrical symmetry, which is how we kind of associated with it. It's when, yeah, because I talked about how the Wall Street, financial capital moves through an economic system, and by the same mathematical equation, that smoke particles or vaping particles will diffuse themselves through the air. It's called the diffusion equation. I think I wrote down the 4 themes in. By the way, if anyone else, if you have that in your notes, you could tell me, um, just to make sure that I did tell you before. Wow, what is it? Why is it such a? Don't have my mechanics notes here in front of me. And this is not something you want to see in a book. This is just my own thing that I've associated with. Teaching. Well, look, they'll come. Let's just deal with the symmetry. So what I wanted to point out is the symmetry associated with these fields. Yeah, in chapter one I did, but it's not in chapter one. That's something that's coming from my notes, but I mentioned it when we did the first week of class. So if you were to look at the gravitational field of the Earth, it was discovered by Isaac Newton. I told you Isaac Newton contributed three things. Oh, there you go. The others are perspective and technique. Thank you very much. Yes. Awesome. So we did talk about perspective. That was the poet and the space, the poet and the astronaut. I call that's my story. I made up that story, by the way. I'm so proud of it. And I just gave it, I never had a name before. Now I'm giving it a name. The poet and the astronaut. The poet, the astronaut, and the alien. Oh, that's awesome. So proud of myself. Um, yeah, so we talked about that with that story. And what did specific and technique as in problem solving. And we talked a little bit about we won't talk so much about technique and not quantified, but because we don't do a lot of like math problems necessarily in this class, is more conceptual. And the problems that we will do, you won't have to figure out, it'd be pretty much like plug and chug type equations like the ones we're about to write down here. Um, but I have mentioned something about specificity. I mentioned to you that, the question that you ask dictates the answer that you get. So when you're asking a question or formulating a question, it's best to be as specific as possible and to make sure that you're asking the thing that you really are trying to ask. It's not necessarily true when you start to get to complex uh, concepts, right? Anyway, but here I'm dealing with symmetry in the next couple of minutes. The universe is highly symmetric, and it's a characteristic, a property of the universe. What do I mean by what? I've said that before. What do I mean? Well, we know certain artists like have signatures or characteristics, right? That you can, in fact, people say that with an artist, with a musical artist, the thing that they're actually selling is their personality, and you can hear the personality in the way that they sing, the tone, the phrasing, the type of music. But even within a genre, you just the artists who you can actually hear and you can know who they are just by hearing the voice. If you realize those are the artists that are the more famous. People who have generic voices where you can't really tell who they are by the way they sing without seeing them, you notice that they don't do as well. That's because it has to do with specificity, right? Like the more it's very specific to their personality. So ultimately, and I think there was a quote that it's a famous quote that was not that famous, but it's one that I remember. I have to pull it up, but it was by Mick Jagger. There was this article that came out. One of my favorite magazines is a magazine called Vanity Fair magazine. And back, they have now, they have the very famous Hollywood issue every year doing around the Oscars. But they also have a yearly music issue that started around the time I was in grad school. It would have been around 1994, 95, or something like that. The very first music issue of the Vanity Fair magazine featured, well, a few artists, but one of them that it featured was the Rolling Stones. And it was publishing for the first time pictures that the famous photographer Annie Leibovitz took of the band on their first American tour 30 years before. And Annie Leibovitz, who was not famous at the time, traveled with the band across the country in the late 60s on their first American tour. And they were publishing the pictures for the first time. And they interviewed. I think there was also an interview. I don't know why it was never published back then, but it was being published in that magazine for the first time. And one of the things that I'm kind of into music, and I kind of write and sing and play a little bit. Never pursued music professionally, but I'm definitely have always been into music. And one of the things that at that time I was kind of I was writing some of my first songs and just trying to figure out, how to write and just whatever. And I was kind of starting to kind of perform out, to it. Anyway, Mick Jagger said something about how he was so insecure in the first part of his career because he sang off tune a lot. And then I kind of laughed to myself, like, wait, actually, Mick Jagger still sings off tune like all the time. But the thing is, I didn't even I had listened to the Stones my whole life and I never even noticed it. And when he said it, then I went back and looked at a lot of these songs, and particularly like the live songs, a lot of it. And sometimes he is kind of off, but it's like I didn't even hear it until he said it. But it's because he just has a very, like, anyone anywhere in the world would know Mick Jagger's voice if they heard it on a song that not even a song that he's familiar with. It's just such a specific voice, and the way that he phrases things and talks. And that's why they're the biggest and the best, arguably rock band of all time. I mean, they're still going, 60 years or so. And they were a band before I was born, and they're still going, so, and still relevant, actually, as far as I'm concerned. And so, what is it are they selling? It's the specificity of his voice. It has a certain characteristics. It's part of and what he said is, and I can't probably say it exactly the way he said it, but it was something like, the way that he got over that, his insecurity with his voice and being on key, and not being able to sing like someone like an Aretha Franklin, because these were the people that they were studying. They were really into a lot of the American blues music, which a lot of African American people like Ella Fitzgerald, um, Aretha Franklin. They specifically said that they studied these people and just loved their music, and they said it in the interview. Everybody knows this, and like, Mick Jagger doesn't have the voice like an Aretha Franklin, but arguably a bigger, as became at that point he wasn't, but arguably became a bigger star than even someone like, certainly on the same level. Now, so my point is that what he said, it's just stuck with me, because you can say that about music, you say it about anything. And it's a quote, "The thing about music is that you have to get your personality across. F the notes," unquote. That quote significantly impacted me, because I realized that it's kind of a way of saying, just like how we said that the rope here is the medium, but the wave is something different. The wave is the energy that happens to be using the rope to communicate, to flow. You can say that about anything. That's actually an analogy, kind of something you can say about anyone who's good at anything, whether it's artistry or whatever, right? You have to kind of commune with that thing. I take Michael Jordan in basketball, right? Who changes the game, turns it into something that, this beautiful acrobatic thing that no one ever. Why? Because it's like, you take this discipline, you put it into yourself, and then as you begin to learn it, you become one with it. I mean, I know it sounds really crazy, but that's true. And then you begin to change it, because you communicate it with your own medium, your own sensibility, and your medium is everything. It's your body, it's your mind, it's your emotion, it's everything. So that's what Mick Jagger was talking about. That's what an artist does. You take a song and you communicate it with the specificity of your own personality. Why am I saying this? The reason I'm saying all of this now is because you can say the same thing about the universe. The universe has a certain, now, we don't have to get into debate, whether or not, the universe is conscious, or not, there's a God, or not. I'll leave that to you. Whether you believe that or not, you don't have to understand that our universe has definite characteristics that could be described as a personality. At least I see the analogy. There's certain ways in which the universe behaves and does things, and behaves and does things, that if you take several steps back, you could kind of look at it as, when I say properties, it's certain specific things that just repeat themselves over in the manner in which the universe operates. You could then, you know, describe that as characteristics of of the person. Like maybe some other universe doesn't behave that way, and you can kind of begin to look at it, or at least make an analogy that that's a personality. One of the significant aspects of our universe's personality, which I can also refer to just as a property, is the idea of symmetry. It is highly symmetric, and it is a fundamental property of our universe. And once you begin to understand that, then it helps to be able to evaluate our universe, I think, more effectively. One of the biggest symmetries is the functional form, the mathematical form between gravitational force and electrostatic force. And there is no reason why this symmetry exists. We don't know why, like, because these things aren't, because as I said, once we could figure out the grand unification, we could connect gravity with electrostatic or electromagnetic force. To date, we haven't been able to do that. So there is no reason why this symmetry about to write down to you exists other than it just does. And the people who figured out these equations, Isaac Newton for the force of gravity, a guy by the name of James Clerk Maxwell for, sorry, no, he did it ways. Somebody named Coulomb is his last name. His first name is escapes me, but Coulomb's law is the law that defines basically the force for gravitation. And I think he was a Swiss physicist, and his name is first name I forget. I want to say Michael, but he had kind of a long name. But the last name is Coulomb. But it's the thing that this force is the same force that is associated with static electricity and things like that. So the symmetry is that their mathematical forms are very, very similar. And yeah. So I'll put it over here. So Coulomb's law describes the force between two charges, and the universal law of gravity describes the force between the two massive particles. Now, before I write down the mathematical equation, I want to enforce this symmetry by looking at what the forces would look what the field associated with these forces look like. So there's one thing I have to clear up here as well. I know that oftentimes in scientific movies we refer to like in Star Trek, or in a lot of science fiction movies, a force field. The concept of the phrase force field is actually incorrect. There is no such thing as a force field. There is a force that is associated with there's a force, and then there's a field, but those two things, technically speaking, are not the same thing. So let me tell you what I show you. I can illustrate that very easily. So here's a ball, here's a mass, and we know that gravity, and I'll say even reiterate that here, that gravity, the gravitational force arises when you have an accumulation. Well, the gravitational field, I just about to mess up and say what I said doesn't exist. But anyway, a gravitational field exists because of the accumulation of mass. If mass accumulates in a region, then around the space of that accumulated mass, you'll begin to see there begins to accumulate, or there's something called a gravitational field is created. And you can test how strong that field is by taking something called a test mass and putting it in that space and seeing how the collective mass that created the field affects your test particle. The more mass that's accumulated, the larger the field. So the Earth is an accumulation of mass. And right here in the space, just the space of where my hand is, there's a gravitational field there. Now, the problem is you can't actually measure a field. You can't. The only thing that you can measure in a lab is like current, mass, and you can measure force. But the gravitational force on a body that I would place at this point in space it's associated with the field. There's two things that are associated with it that you can associate with the field and to some degree measure. And that is force and energy. If you can measure the force and the energy associated with an object within that field, then you can determine something about that field. But you cannot measure the field directly. You have to measure it indirectly by having a test particle and then measuring the force on that test particle as a result of that field, or measuring the change in energy, potential kinetic, of that particle as it moves along in the space of that field after having established some zero potential energy point, which you have to do. So my question to you is, right now, in this vicinity of space, is there a force that exists in that point? Like at this point, like at the tip of my finger, is there a force there? And I'm not on my finger, but just at the like in the space that my finger is pointing to. So I'll point to it and I'll leave. The space is still there. Is there a force in that space? Yes or no? Tamika, what do you think? Is there a force there? Well, I'll give you a question. And we're assuming it's a vacuum. So we're not talking about the, you know, particles or the atmosphere or anything like that. And Tamika says, no, my answer is correct. No. In fact, if there's nothing in the space, there's nothing to force on. But is there a gravitational field there, Tamika? Is there a gravitational field in the space surrounding yeah. So that's what I'm trying to say. There is no such thing as a force field. That means that there would have to be, I don't know, I can't even explain it because it's counterintuitive. It doesn't exist, right? There's only going to be a force if you place an object in the field at that point. Now there's a force on that object because, and you can think of the forces coming from one of two places, which is the same thing, either the field or coming from the mass of the earth that creates the field. Either way, it's pointing to the same field. It's just two different perspectives of describing the force associated with that field. So the term force field, it implies that there's this space where force exists. It doesn't. Force is only going to exist on an object if it's inside of a field somewhere. So there's no such thing as a force field. There's the field, and there's a couple different types of field that we will look at. There is the gravitational field, as we've said. Now, we've put, in terms of the unified forces, we put them together, electromagnetic. But for the first chapter, we're going to separate them. There's electrostatic field and magnetostatic field. And I'm saying static because these fields, both electric and magnetic, they originate from charges, but they originate from charges that create stationary fields where the fields are not moving. Once the fields start to move, that's how it creates an electromagnetic wave. So, gravitational field. In fact, we refer to these things as conservative fields. And to our knowledge, there's only 3 conservative fields that we know of. Gravitation, I think this is probably not in your book, and at least not in this chapter, but it's good to know and to kind of facilitate, kind of build out the chapter. Gravitational field, electric. And I'm going to continue to use the word electrostatic because it means it's a charge that's not moving. Electrostatic, or at least not translating, let's put it that way. Electrostatic field, and magnetostatic field. Now I want you to take a look at these two and the idea of symmetry. So if I were to draw a little Earth here, and forgive my artwork, but yeah, whatever, that's the Earth. I could represent the field. We know that it points, basically the field lines, they have to be perpendicular to the Earth, but because the Earth is round, perpendicular to the surface of the Earth. So right now, gravitational field points straight down and would hit the Earth, kind of make a 90-degree angle if I look at the field line going into the surface of the Earth. Now, it looks like the Earth is flat, but because the Earth is curved, that means that we call the pattern of the field lines, we say that they are radial, meaning all gravitational field lines point toward the center of our lovely and beautiful Earth, Mother Earth. Mm. We know gravity is an attractive force, so it pulls things toward the center. And just from our vantage point, that feels like down toward the surface. So the field has a specific direction. And that's, we refer to it as an attractive force because any accumulation of mass, even you and I, if you and I were out in space, because our bodies have mass, we have a gravitational attraction toward one another, and we would begin to pull one another toward. Like if we were out just in space over time, what we would see is that we would pull, even if we were just floating out in space away from any large bodies, just floating there, what we would see is that we would begin to move toward one another because our gravitational attraction. So this is a force of gravity, and I'm going to call it small g, as in the universal, the acceleration due to gravity. Yeah, now it's an attractive force that points in. Now here's the thing. I'm just going to draw, we know that positive charges are protons and negative charges are electrons. We generally represent them also as very small uh, bodies, like circular kind of bodies. So I'll just do that. Now I'm gonna make these, we call them, when we think of positive charges and negative charges separately, we call them monopoles, mono meaning one, pole meaning the origin of the field. And the way that a massive round body is the origin of a gravitational field, charged particle is the origin of an electric field. But for a positive charge, turns out the field, it also is a radial field, but it points away from the charge. So the positive charge here, the proton, would have a field that points still radial, same shape, and that's the symmetry. That's asymmetry, but it's pointing away. Now this isn't force now, this is just the field. And we refer to that as E, as the electric field. What about a negative charge? And remember, I told you that the value of the charge is the same for both an electron and a proton. And the symbol that we use for that is kind of like a script, an E. It's called the elemental unit of charge. It doesn't mean electron. Don't confuse it. It's not an E. It's kind of a weird looking E. And it's the magnitude of the charge, which is what is it? 1 point, wait a minute, oh gosh, times 10 to the negative 19, 1.6010, 1.601, what? 1.60 times 10 to the negative 19 coulombs, right? Am I missing something? They're probably going to do 3 significant units, but let's see here, right? Well, they just do 1.60, so I'll just do that. 1.6 times 10 to the negative 19 coulombs. So it's the same for both positive and negative elemental charge, not electron. So the electron then, the negative charge is, it turns out that that also has a field that points radially inward. So it looks very similar to that of the Earth because it's radial, just like all of them, but it points in. And then we got a break coming up here in a minute, so we'll take a minute here momentarily. Let me set this up so you can maybe think about it during the break. Now, radio means that the language. Radio means that if I were to connect, continue the line of these field patterns, they would go to the center. They would all collapse at the center of the part of the object. So that's what the term radio means, right? Radio means field lines connect at the center of the, either connect or originate from of the originating particle, body. Okay, the term radio. So we went 4 minutes. So yeah. So what I want to point out before, as we go into break here, is you can start to see the symmetry in the fields of these. Even though the gravitational field is different from the electric field, they clearly have some sort of relationship mathematically that's something similar. So that's the beginning of looking at how these things, even though, again, gravity, we still have not associated it in any way whatsoever, theoretically, connected it with electricity, electrostatic force, but clearly they have some similar things. Which why does the universe do that? Why, if you think of it as a characteristic, the universe has a choice. It didn't have to create gravity like this, or have electrostatic force look like that. It did that for a reason. You might suspect, and I know I'm kind of personalizing it, but I think that's one way of looking at the universe. Even if you don't consider it to be conscious, still, why? Why does it do that? Something to look out for. That's what I mean by symmetry. Now, the geniuses who figured out these force laws associated with these fields, the symmetry, it gets even more specific and obvious. So let me just write them down, because they don't actually write them down in symbols. I think they just they write down words. But when you see the symbols, that's again, mathematics is a kind of language. So when you see the mathematical equations for these formulas, the symmetry begins to jump out at you. So Newton, again, universal law of gravity, universal gravitation, discovered by Isaac Newton, and published first in his book, The Principia, in 16 something. I want to say 1683. Hey Siri, when did Isaac Newton publish The Principia? Oh, I was close. What did I say? 1683? It's 1687. Okay, I have to get that down. Um, yeah, so the universal law of gravity is that gravitational force, I'm going to put an F sub G here, representing, is equal to the universal gravitational constant G times. So let's say that we have two massive bodies. So this would be like if I have, a mass 1, M1, and a mass 2 over here, M2, separated by a distance R. R, when we start to talk about spherical bodies, the general variable for distance we like to use is R, not X, which you do X and Y like in like algebra and stuff. We use because it comes from this idea of a radial distance. So like if I'm at the center of this object and I go out a distance R away from that object, like basically that distance would make a circle because no matter what direction I am, I could be the same distance away from the center. So we refer to it as the radial distance. And so that's really where the variable R comes from. And we use. So they're separated by a distance R. The force between them is going to be determined by the product of the masses, M1 times M2, divided by the square of that radial distance. And Isaac Newton, again, sometimes in physics, we have certain theories or concepts that kind of we can develop as a theory that leads to a particular result. But sometimes in physics, there's just a basic fundamental quantity that describes the characteristic of the universe where there's no lead up to it. You just have to look at the universe and just guess, figure it out. The universal law of gravity is one of those things. There's nothing, no build up or set of concepts that leads you to this relationship. You just have to, or even the fact that the same thing that pulls an apple out of the tree is the same thing that keeps the moon falling around the earth, or the satellites, because they did know of Halley's Comet even back then. In fact, Halley and Isaac Newton were contemporaries. They were friends. They knew one another. In fact, Halley is the one that came to Isaac Newton and asked him, did he think it, did he know what was causing Halley's Comet, to, what the forces were? And Isaac Newton actually has a very good point. Do you know the television show The Cosmos with Neil deGrasse, the famous physicist Neil deGrasse Tyson, Dr. Neil deGrasse Tyson, where yeah, okay. Oh, you don't know that? Oh my gosh. Oh, there's 2 seasons. So there was a famous physicist in the 70s, Carl Sagan, who, when I was a kid, he created this show called Cosmos. And it was a really good show, and I think it just went, I don't know, maybe 1 season or so. I don't remember the seasons. And it would come on like public television. I didn't see much of it. I saw a couple episodes back then. Well, they brought that back probably about 15 years ago, maybe 20 years ago, maybe 15. And with Neil deGrasse Tyson being the narrator of the show, it's really, really good. You should definitely. And there's only 2 seasons. I don't know if they come out with a third. And they come out with it like they didn't come like year after year. And I think there's like 8 or 9 episodes in the first season, maybe about the same in the second season. You definitely want to take a look. You can find it on YouTube, maybe some streaming service. I don't know, but it's really, really good. And in the first season, they talked about how Isaac Newton came up with gravity. There were several physicists, So I think it's you should probably look it up. It's the episode, maybe episode 3, I think. And it was something like When Science Conquered Fear is the name of the episode. So go ahead and check that out. Cosmos first season. Well, the new Cosmos, the Cosmos with Dr. Neil deGrasse Tyson. I don't know how you spell that middle name. DeGrasse. I know it's two words. I don't know how you capitalize. Whatever. Tyson. And and I think episode 3 of season 1. So season 1, episode 3. When Science Conquered Fear. And it tells the story of. It's a fascinating story. Really, really good. And they have like the we're getting near the holiday season. You know how they have these animated stories a lot of times during the Christmas season, Thanksgiving. Um, and they animate the story and they tell the story. Well, they'll switch these animations where they dramatize the story. I love that kind. I love that. I love that stuff, that kind of thing as a kid. And they do it with this. It's really, really good. So check them out. In fact, that season, I like the first season better than the second. It's really good. So definitely worth, even if you have to maybe buy maybe for a temporary period do a streaming series. Sometimes they give you the like a week grace period or a free trial for some of these streaming services. So if you can't find the whole thing on YouTube, but you might, it's worth uh getting a streaming service to look at the first season at least. um well, he figured that out. It just And so what I'm trying to say is that there's nothing that comes before this. Isaac Newton just thought about it, looked at stuff, figured it out, realized that the same force that had Halley's Comet associated with the Earth was the same force that held the moon, same force that the sun, the planets around the stars, because it's not obvious. I mean, now we take that for granted. But before Isaac Newton, people didn't know. Like, it could have been two different forces, like He had no idea. But gravity is that force, and it does all of that. It's the same force that pulls an apple out of the tree. Now we take it for granted because we know. But Isaac Newton, at least in modern times, maybe people knew it back in the antiquity someplace, and we lost that knowledge. Could have. You can't take that for granted because, as I think you do know, but there was this library at Alexandria, Egypt, that was destroyed during the Roman Egyptian wars or whatever those, yeah, back in 300 BC or something, and it housed all of the knowledge of the known world, the Western world or known world up to that time, and so who knows what but according to conventional history and science, we are the pinnacle of our knowledge. And one of the things that got us there was certainly Isaac Newton's contribution of the universal law of gravity. So, oh, by the way, I should write down that G is equal to 6.67 times 10 to the negative 6.67. G 6 point, what is it? Yeah, 6.67 or 6.7 times 10 to the, no, negative 11. Sorry. So G, put that here somewhere. G is equal to 6.7 times 10 to the negative 11. And the units are newtons meter squared per kilogram squared. Yeah. So I'll box that in. I know I'm keeping you over here. Some constant here. But I do want to say this before I let you go. So if you just know the two masses between two objects and the distance that those objects are away from one another, and then of course you have the constant here, just stick that in the formula and do a calculation, and that will tell you the gravitational force between those two objects. We'll do that when we come back from lunch to compare it and show you how weak gravity is. Now, your weight, your weight is basically the gravitational force between you and the earth. So if you figured out, now that's an interesting thing to do. Maybe we can do some of that when we come back. We can figure out how, what our weight is by putting in your mass, and the r in that case would be your distance from the center of the earth. Since we're on the surface of the earth, this r would be the radius of the earth, and that would pretty much estimate what your weight is. Now you'd have to be careful because the units would be in newtons, not pounds. So for example, I'm about 175 pounds, and I won't give you the conversion relationship, you can look it up, but that's approximately 80 kilograms. Now, we also know that you can determine someone's weight from Newton's second law, right? The weight of an object is also equal to the mass of that object times the acceleration due to gravity. What I'm trying to say, if I use Newton's second law through the definition of weight to calculate my weight, but I also use this formula where this is the mass of the earth, this is my mass, and this is the radius of the earth, those two numbers would be the same. We could prove that, right? Approximately the same. So what this actually is doing is measuring the weight is just the gravitational attraction between yourself and the other object. In our case, it's the earth. And by the way, I don't know if you knew this or thought about it, because of the second law, that gravitational force, that your weight is the attraction of the earth on you. So in my case, I'm 80 kilograms. G is 9.81. We know that, right? G is 9.81 meters per second squared, which if I round it off, that's approximately 10 meters per second squared. So if I wanted to use that approximation, I could get a very quick estimation of what my weight is in newtons, because I'm about 80 kilograms. G is approximately 10 meters per second squared. So my weight is approximately 10 times 8, or 10 times 8, 80, which would be approximately 800 newtons. So my weight is, at 175 pounds, is approximately 800 newtons. And so what I'm telling you is that if I took my mass, 80 kilograms, the mass of the earth, we can look up in a book, the radius of the earth, we look it up, put that in, that's going to be approximately 800 newtons. So that's the connection between Newton's universal law and just what we consider to be the formula for weight. They're basically two perspectives of the same force. Well, maybe we'll stop there and take the 15-minute break because I'm getting on into it. But when we come back, again, I was pointing out the symmetry between Coulomb's law, the law that describes the electrostatic force, like this force between two charges. Well, what would that look like? And the gravitational. We've already seen that they have a symmetry associated with the field pattern, the lines of the field, and that should be reflected in the formula for the magnitude of the force. I need to put something over here that I didn't. I'm going to go ahead and do it. It's usually we do it for an advanced class, but I'm going to do it here. Or should I? You know what? I don't think your book does it, so I'm going to do it. I'm going to take the force is a vector, so we could describe it as a vector, but I'm going to take away the vector representation so that I don't have to put something over there called a unit vector. So that's just the magnitude, represents the magnitude of the gravitational force. I did the same thing here. Let's just do the same thing here. Magnitude of the weight is equal to mg. Box that in. So you might try that. You might try. In fact, let me go ahead and see if I can find the mass of the Earth and the radius of the Earth. And we can. Yeah, you should be somewhere in a table here somewhere. So maybe you could do it yourselves and calculate your own weight in newtons. Here we go. So the mass of Earth is 5.97 times 10 to the 24th, is it? I think so. Kilograms. Sorry, man. Yeah. I want to keep these field things up, so I'm gonna be careful about how I erase this. Um, mass of the Earth, 5.974 times 10 to the 24th kilograms. Pretty massive. And the radius of the Earth, just in a chart in the back, table in the back of your book, properties of planets. The Earth radius is 6,378 kilometers. 6,378 kilometers. 6,378. So you have to convert that to meters. So that's going to be 6,378 times 10 to the third meters. So, and you might want to, the problem is like when you look in a book, that's another confusing thing we do in science. They might give you a conversion relationship between pounds and kilograms. That's just a shortcut because those it's like comparing apples and oranges. I don't really like to do that. And I don't want to really get into you know, yeah, I guess maybe I could, but um, yeah. So I won't say anything about that at the moment. So yeah, well, you could just, I guess you would have to know what your mass is, and again, weight and mass are not the same thing. Um, but you could estimate, you could approximate, I guess, if you didn't know. I guess I should tell you how to. There's probably have some conversion relationship in here somewhere. I haven't seen it in the book, but again, it's not really the same thing. Mass and weight are not the same thing. So you have to kind of do some dimensional analysis, which I did show you how to do in terms of figuring out what your mass would be. Well, I guess you could just do it from there. Like if you, yeah, that would do it in kilograms. Yeah, it's very easy. So if you wanted to know what your mass is, you just take your weight and divide it by 9.81. That's all from this equation. So whatever but again, your the weight is going to be in pounds, so you would have to convert the pound. That's what I should do. You have to convert the pounds to newtons. So we could do that. So the conversion relationship is that what is the relationship between newtons and pounds? And I don't have that memorized. I guess I could find it somewhere. Uh, maybe Siri can tell me. I'll look it up. Hey Siri, how many pounds is in a Newton? So 0.225, I think I knew that, pounds in a Newton. So you could use that relationship. You could do that. There are 0.225 pounds equals 1.0 newtons. So, so for example, and I could actually prove it. I said my mass is about 80 kilograms. So if you take, remember you could do the dimensional analysis. If I'm 175 pounds, how many newtons is that? Let's do it here. Remember, I told you how to do that. So starting with 175 pounds over 1.0, make that a fraction. Then you have to convert the conversion relationship to 1. So in this case, I want to get rid of newtons, get rid of pounds and make it be newtons. So I divide both sides of this by newtons. So that would be 0.225 pounds divided by sorry, the other way around. I divide both through by pounds. So 1.0 newtons is equal to, or divided by 0.225 pounds. So the pounds will cancel, and that's going to give me whatever newtons it would be. So divide your weight by 0.225, and that's going to give you what your weight is in newtons. So I don't know what, let's see what that would be. My calculator. Guess I could use my iPad. Wait. Yeah, so it's off a little bit. It's like 777. I said approximately 800. Well, first of all, I didn't use 10. If I used 10, it'd be well, it wouldn't be what am I saying? No. Sorry, that's something different. Yeah, so my weight then, that's approximate, if I round it off, it'd be rounded off. So that's about 777, but not quite 800, but you know. But again, I should put I could I if I approximated with 10. I can go back and put in the 9.81 and see what that would be. And but this is 777, actually approximately 778 newtons. Now, if I was more specific, it would be approximately 80 times 9.81. So 80 9.81 times. So that's actually closer. That's actually gives 784. So I'm not that far off. So it's, um, yeah, it's approximated because I'm approximating. Yeah, I mean, I'm probably not, whatever. So this is how you do. So basically, if you wanted to figure out what your mass is, you would know your weight divided by 225, and that's the thing that you would use in these equations. So here it would just be your mass times, well, of course, that's just the reverse of this, but you could use the Earth's mass and your mass in this equation and show that it would come up with the same number here, or close to it, approximation. All right, so we're at the top of the hour. That's a pretty good point to break, I guess. Should have done it 30 minutes ago, but whatever. So let's take I need a little bit more time. Let's take about so this you could do like a working break where you kind of play around with this formula, maybe do what I said. Figure out what your math is using this relationship dimensional analysis by dividing by 0.225. Um, and then uh, plug it into that formula to see if it gives you the same something very similar to what you get when you use Newton's laws. And again, um, yeah, um, you could verify what your mass is by what your weight is by using this formula here, and then see that that gives you the same relationship when you do that guy. Yeah, using the same mass. Other things you could do is, I could compare how much gravitational attraction of someone who is my mass would have on me just by using my mass here for both masses. Like, what if there was another person? And the standard we use is the distance away would be 1 meter. That's the kind of thing they work out there in the book where they have two masses a meter apart. But you could do that with any two masses. You could do it with like the average mass of a man. So, what is the gravitational force of someone else on me if they're a meter apart from me? Um, that's kind of a standard way. And also, what we really want to do is we do it with elemental particles. Like, once we have this formula, we can calculate the gravitational attraction of one proton on another proton when they're a meter apart. But we also know the mass of a proton. Sorry, we know the mass of protons, so we can do that. But we also know the charge of a proton. So when I write down Coulomb's law, we can compare the force of attraction of electrostatic attraction between them. And that is actually a way of comparing the relative strengths of gravity versus electrostatic force, because these are elemental particles. So these are the particles that everything else in the universe are made of. So it gives you basically a fundamental understanding of the relative values, the relative strengths of these forces. We'll do that when we come back because they do not do that in the book, I don't think, and it's aware. But you want to get familiar with the formulas first. So this is a way of getting familiar with the formula by using, calculating these gravitational forces. Okay. So before we get too much, let's go ahead and break now. So we'll come back 20 after. All right. Bring it back. Excuse me. What was I going to do here? um, oh, so write down Coulomb's law. Well, Coulomb's law, you're going to see that it has a very similar mathematical form. Uh, you can hear me, right? Oh, I did it with my weight. For example, I weigh 128.6 divided by, yeah, thank you. So be careful. Now that is your mass, but that's not in kilograms because in fact, actually that's nothing because you're mixing systems. You have your weight in, I'm assuming that 126 is pounds, right? So you have your weight in pounds, which is English units, and you have G in in metric units. So that's not going to work. That 13 doesn't mean anything. If you want to do it that way, which you certainly can, let me try to work with you on that. Uh, in English units, G is 32 feet per second squared. So you'd have to go back and do that again. And that will give you your mass. And I forget what the unit for mass is in English units. Uh, I forget well, I guess you could work it out and see by unit analysis, but it's not going to be kilograms. So you got to be careful about that. Hey Siri, what is the unit for mass in English units? Okay, that's not English units. Hey Siri, in English units, what is the unit for mass? Okay, so he's off. Yeah, I can go to the internet. English unit for mass. Huh. Is that true? That can't be true. It has to be something else. Um, Kilograms is the metric system. What is the okay, I think I found it. I think it's something called a dram. Yeah, maybe that's even weight too. Not bad. Yeah, I have to research that. But I don't even recall. I don't think I've ever done it. I figure it out in. What I would suggest is the following. I can, yeah, information program, yeah, yeah, but that there's something off because that's I know that's it said kilogram in English, but that doesn't make sense because you can't have, or maybe maybe it's defined that way. So pounds divided by feet per second squared is kilograms, but that no, it's got to be some because it can't be. You can't have two units having same definition for two different units. I mean, or maybe you can, but they should. That means that so let me just work something out real quick. In units, in English units, a Newton is a kilogram meter per second squared. That's a Newton. All right. So if I do a unit analysis of weight, so a Newton is equal to by units Newton second law, kilograms meters per second squared. So then, yeah, you just get kilograms equals kilograms. So if you divide a Newton by meters per second squared, that equals kilograms. That's true, right? Because, yeah, so kilogram, you substitute that in, you're going to get kilograms equals kilograms because kilograms will divide out. Okay. That goes, and then you just go. Right. So what about if you did it in English units? Maybe you're right. Maybe Siri's right. Maybe I'm wrong. I don't I haven't thought about this. So you'd have a pound then. So basically force is pounds. It's going to be the units weight is a pound. Keep that kilograms, and then this is going to be meters per second squared still. Sorry, feet per second squared. Well, they you define a pound clearly by Newton's second law. Yeah, I guess you could if you keep. Yeah, because I've only ever seen mass measured either in grams or kilograms, but that's the same unit system. So yeah, I guess maybe that's why I never. So then a pound is defined as a kilogram foot per second squared. If that's the case, then that's true. And I don't really know any way else to the maybe, yeah. Have I never thought about this before? Maybe, because there's never no reason to use English units. I just always assumed that they were, yeah, but I guess, yeah, you look on any scale. I've never seen a scale measured anything other than grams. And so there is something called a dyne, D-Y-N-E. Hey Siri, what is the unit of a dyne?
The dime in United States usage is a 10-cent coin,
Oh
1/10
God.
of a United States dollar, labeled formerly as
Hey Siri, stop. What is a dyne? Okay.
the answer is
No.
from Collins Dictionary.
D-Y-N-E, dyne, is a unit of force in what I was taught English units. So let's see here. So that's why I always assumed that if the force changed and the acceleration changed, then the mass would change to a different unit either. I just never wondered what it was. So what is a dyne in base, BA units? A dyne is 10 micronewtons. Huh. The dyne, Greek symbol, is a unit of force specified in centimeter, gram, seconds. Okay, that's not really, that's still unit. I thought, okay, that's still metric system. So no. Well, okay, you know what? Maybe you're right. Maybe it's just a kilogram. And a pound then would be defined as a kilogram foot per second squared. Okay, fair enough. All right. Well, I still think you got to be careful with the calculation that you did there because um, you definitely can't have, uh, you'd have to make the conversion of, according to this definition, you would have to still convert. Actually, that's a way of testing to see if this is true. You would
So
have to
I would
convert.
so I would have to basically break it down a little bit more.
Well, you just would have to use 32 point feet per second squared as opposed to 90, as opposed to 9.81,
Gotcha.
if you're going to use pounds over there.
Okay.
I'm pretty sure. Or what? Actually, the better, I would just, I probably would just convert my pounds to newtons. That would be what I would do. So you can look up that conversion relationship anywhere. There's definitely a straightforward conversion. In fact, they should have it in a chapter somewhere. Let's see. But you could find it in a chart. Let me just write that down for you. That's probably the best
Okay.
one. Let's see. It would probably be in one of the previous. They introduced the Newton's laws, but let's just. Or you could ask. So I'm pretty sure Siri would know. I think it's like. Oh, I've already done that. It's right here. Sorry. Duh. So, sorry. Yeah. So convert your weight. So just basically put in one. So that would be 128.6 divided by 0.225, and that's going to give you your weight in in newtons. What is it? 1.28, 128.6, 0.225. So your weight in newtons is 570, approximately 572. Approximately 572. Now, what you want to do is use 572 newtons as your weight, as opposed to 126.6, 128.6. And now you can divide 571.55 divided, well, approximately 572 divided by 9.81. That will definitely, without a doubt, give you what your mass is in kilograms. So dividing by 9.81. Oh. So your mass is actually 58, 58 kilograms. And that's I've taken the two significant digits, so there's some rounding going on there, but approximately 58 kilograms. Does that make sense? And that actually is more reasonable, because 13 was too small, very much too small.
I like how you were able to break it down, so that was pretty interesting.
Okay. Yeah, that's the way that I would make this conversion. I think and the interesting thing is that if this is a true relationship and we don't have to convert mass to some other units, which
Mhm.
I thought we did, then it should still work for the same. In other words, if you divide 128 by 32, I know you're not going to get 50. So that's a problem there. But that's what
Yeah.
you should, yeah. So that's that's a problem. So I'm not sure. I think maybe I'm not asking Siri the right question, but then I don't know what I can't find it anywhere. And I've never, I guess I'm thinking about it now. I've never actually done that. I've never tried to convert mass to something other than metric units. We can do it. Yeah, I don't know. So right now it's baffling me. I'm having a brain fart. I don't know what the equivalent would be, but kilograms is definitely a metric system. So I don't know what mass. I'm drawing a blank. I don't remember. I've been doing it for so long. I don't remember if I ever knew how mass was measured in anything other than metric units. I literally remember when we went to the metric system. I think I was in the third grade. It was 1970. Because before then, no one used meters or kilograms or anything like that. But I wouldn't have any reason until I got to high school, maybe even college, of measuring mass. Maybe my physics class in high school, I don't remember we just did it in kilograms, I think. But I think we were using metric. But I don't remember what people even referred to. We just said weight, right? Like you just didn't do the math. So I don't know, which is kind of a hole in my knowledge. So something's going on there. I got to figure that out. So I apologize. I just never thought about it. All right. Anyway, that's the way I would do it. I would convert and I guess that's the way I've always done it. So I would convert the weight to either English units or metric system, and then from there, convert, see what the equivalent, see what the mass is, and then use mass in metric system. All right. So the other thing, let me have you do this. So that is what your 58 kilograms. Yeah, that's what your mass is. Why don't you, I want you all to, so the other day we determined what the mass of a electron was and the mass of a proton. What I want you to do is to go ahead and calculate the force between two protons by using this formula, and assume that they're 1 meter apart. So use R for 1 meter, look up the mass of a proton, and figure out what the force, gravitational attraction, is between two protons that are 1 meter apart. Go ahead and do that now. I got to take a quick break. information about mass. Mhm. Slug. That's what it is. A slug. SLUG. Okay. Man, I'm getting old because I knew that. I just could not remember. It didn't even occur to me. A slug. That's what it is. So that's English units for mass. Yeah. So I believe that if you have, if you have there's a way I could test this. There should be a conversion from slugs to kilograms, and it should come from that definition. Yeah. So if you have your weight in pounds and your acceleration in feet per second, then your units for mass should be something called a slug, which we don't use any. Well, it's true, but we don't use English units anymore. That's what it is. So I can test this. So what was your weight? 120, 126, 128.6. I'm going to be a bit more specific. So 126 pounds. And this is slugs times 32 feet per second squared. So then your mass in slugs should be equal to 128.6 divided by 32. And that's going to be equal to 128.6, 32. That's four slugs. 4.01, well, 0.02. I'm gonna, if I were reporting, I would round it off to 3 sig, but it takes out that far. So I'll round off at the end. So now, if I want to, there is a conversion relationship, and this, I think this is going to work. There is a conversion relationship between slugs and kilograms, right? One slug is equal to 6.852 times 10 to the negative 2 slugs. So that's a slug. So if I use dimensional analysis, I should be able to convert that and come up with the number that we came up was like 58, I think it was for you. And that would prove that this is a correct formula and that this is the units that you should use. So let's see if we can do that. And that will solve that mystery. And I will redeem myself. So if I convert slugs, so I have 4.0188 slugs, and I want to go to kilograms. Make it a fraction. And the conversion relationship is at 1 kilogram equals 6.8 2 times 10 to the negative 2. Right, 852 times 10 to the negative 2 slugs. Doesn't look like that's going to work out, but that should give me like 28 or 24. And 10 to the negative 2, though, also is 685. Okay, we'll see. I don't know, whatever. So, yeah, so if I have slugs and I want to get rid of slugs, then I have to divide by this number. So that's going to be, right, because remember I told you divide by 1, and that will give me, so it's going to be in 1 kilogram then, there is equal to 6.852 times 10 to the negative 2 slugs. So the units of slugs will cancel. And when I multiply that out, that's going to be, well, we'll see. So 4.0188 divided by 6.852 e to the negative 2, 6.852. And bingo, that's it, 58.6. Now, I think we rounded yours up to 58 because there's some round off error in here I have instituted, but that's, I'm convinced. So it's, approximately, we'll just say approximately 58. Approximately 58 kilograms. Kilograms. Yeah. So if you wanted to do it the way that you did it, you can't use you don't use, you would your weight, your mass would be in slugs, and it would be only 4.018, not the 13 that you had there. And the conversion relationship between slugs and kilograms is this thing right here. Okay, so I knew we could do that. I knew that was, I just didn't remember. Okay. Well, that was a bit of a diversion, but probably worth it. So does that make sense? Do you understand what I was saying there, Julia? I think it was Julia.
Yeah, I understand it.
Yeah, good. But we generally stay with, we generally use the system international is the International System of Units, which is the metric system. So probably, even though I do remember this now and we got this, I would probably convert your pounds, your weight to newtons, and not even worry about slugs, because you'd have to convert it back anyway, because we always deal with SI units. So that's
Right.
the way I would go, is I would just and that's a more common conversion relationship between pounds and newtons, as opposed to dealing with mass. All right. All right. Yeah, it's SLUG. It's not a what's it called, anagram or whatever. It's not that. It's just a name. I don't know why we don't use it anymore. I don't know where it came from, but SLUG, slug. Yeah. SLUG with no periods or anything. All right. Yeah, so let's, still hadn't gotten to what I wanted to finish up with. So Coulomb's law, that's going to be the law between charge. Oh, by the way, I don't know if you did that. I'll let you. I'm kind of about to run out of time, so I'm going to go ahead and write this equation down so you get that, because we want to try to at least finish up this chapter. We want to get any farther behind. But maybe we get into sound a little bit and magnification. Well, we'll catch it up. We'll catch it up. I'll do it. So this is Tuesday, I have Thursday to go. Yeah, I can finish. So the Coulomb's law is the force law between charge. And uh yeah, so Coulomb law, and I'll write them down kind of right beside one another. So it's the force between charges, electrical charges. I'll say E for the electric field. And that is equal to something called a Coulomb constant. And the symbol that we use is K sub E. So it's equivalent to, it's analogous to G. And that's equal to, and this is between two charges. So it would be analogous. Like if I had charge 1 and charge 2, one, let's say 2 protons. So a proton and another proton that's separated by 1 meter. Then, so you can see the analogy between two masses separated by a distance r. So that's equal to the Coulomb constant times the value of the charge, Q1 times Q2. And Q is just a symbol that we use for charge. I don't know why it's Q. Just any general charge. I told you the symbol for a specific charge, the charge of a proton or an electron, was this kind of script E type thing, which I could put up there since this is the problem that I'm using, but this is the general formula, not a specific charge, but a general charge. So Q is the terminology that we use, or the symbol that we use. So two different charges divide, just like M is what we use for mass. I don't know why Q. Probably because, yeah, whatever, because they have protons, they're different things. And mass is just mass, but whatever. Divided by R squared. So look at that. You see the symmetry in the equations? The mathematical form of the equations is they have properties that are similar. It's divided by the distance between them squared. It's proportional to the square of the charge in this case, as opposed to the square of the mass in the case of Newton's law. Look at that. That's beautiful symmetry. Now, the point is like we take this thing for granted now because we know these equations are true. But think about this. Why would, like, the universe is doing this? This is a property of the universe. Why would it go to the trouble of making these two forces, of which we don't even know the relationship yet, still now, which they're not connected, to have this a similar kind of form? And the big thing of this is that the two big properties is that the forces are proportional to the square of something fundamental and intrinsic about that the electrical property of that object, which in this case is the charge. And this law is something called an inverse square law. It's a big thing in physics where the force, of course, you would expect the force to decrease as the charges get farther apart, but it decreases how? Linearly, quadratically, some other power function? Turns out it decreases by the inverse of the square of the distance. So it's a very, very specific and interesting relationship. And it just so happens that gravity, which is a completely different force for, we think, completely different reasons, at least for now, also abides by an inverse square law and is proportional, is inversely proportional to the square of the distance and proportional to the square of a property that is intrinsically associated with the value of that object, and that therefore is mass. In other words, an intrinsic property. That's something that doesn't change no matter where you go in the universe. Meaning, my weight, I'm 80 kilograms on the Earth. My weight is 175 pounds because of the gravitational attraction of the Earth. If I go to the moon, my weight is going to be less, 1/6 the weight on the Earth, whatever 175 divided by 6 is approximately. But you know what happens to my mass? It doesn't change. My mass on the Earth is still 80 kilograms. That's why that's when I use the word intrinsic, it means it's a property associated with that object that is the same no matter where you are in the universe. Mass is a property like that. But another property that's also like that is charge. If something has a certain charge on the earth, everywhere in the universe is going to have that same charge. So that's an intrinsic property, something that uniquely defines that object. So it turns out that these two forces, again, which we don't know the relationship between them, they both have an inverse square law relationship, and they both are proportional to the square of a property that's intrinsic to them. That is what I mean by symmetry when we're looking at the universe. And that is a property of it. Like our universe does this kind of thing all the time. Everywhere you look around, it's beautifully symmetric in that way, not just geometrically, but in the way, quantities interact and things like that. So, yeah. And this Coulomb constant, it's equal to 8.99 times 10 to the ninth Newton meters squared per Coulomb squared is the value of that constant. And again, they should have that. That's in this little exercise they give you here. You can see it there. What's chapter is this? 5. Yeah. Well, they rounded off to 9.0, but whatever. So you could use 9.0 if you want as a round off. So that's the Coulomb constant. So, you could then, so basically now we have a way of comparing the forces, gravity to electrostatic, because we also know the charge of a proton. So we could figure out what the electrical force is and by the way, since these protons are the same charge, like charge repels, unlike charge attracts. So these charges want to move away from one another because of the electrical charge, and they want to be pulled together because of the gravitational charge. So which one wins? Which one is stronger? Or are they equal? Do the protons move together, or do they move apart, or do they stay 1 meter if we were to put them 1 meter close? What we're going to see very quickly is that they move apart with a high acceleration because the Coulomb force is much, much stronger than the gravitational force. So let's calculate it right now. Let's calculate it. So what we need is the mass. We just need the mass of a proton. And I wrote that down for you the other day. I think it's 1.67 times 10 to the negative 27 kilograms. We can look that up. Well, they have it here. Yeah, they 1.7 times 10. It's actually 1.67, but whatever. 1.7 times 10 to the oh, maybe that's what they're doing. The force of gravity between two particles in given a Newton. Well, they don't tell you, but that's weird. They should tell you. That's actually what this this is what they're doing. Okay, well, yeah. They are actually doing what I was so I don't have to do it because it's right there in the book for you. I didn't actually realize that's what that was. So that's what they're doing, because that's the standard thing that you do. You could also do it with electrons, but they're doing it with protons because protons are much more massive. But it'd be nice to do it with electrons too, in which case the electrical force wouldn't change, but the mass of a proton is 9.01, I think, times 10 to the negative 31. So I told you the other day that one is 10,000 times more massive. So it just means that the gravitational force would be even weaker between two electrons. But you could see it right there. So I'll just have them just go through it. You look in when they put it in and they calculate it, you get the gravitational force to be on the order of 1 times 10 to the negative 27 newtons. And negative 47 newtons. Negative 47. I can't even imagine how, like, yeah, I don't even know. So 800 newtons, the force of the earth on me 800 is 8 to the 2, 8 times 10 to the 2, to the positive 2. That's the force between gravity and that Earth had between me and gravity. But 2 protons, the force between them is 10 to the negative 47. That's how much weaker the force of gravitational force, 2 protons on one another, as opposed to now that's not comparing that's kind of apples to oranges, because clearly I'm more massive than a proton. And also I don't have a charge, so you can't really compare it to me, but it does start to give you an intuition about what that means, right? Like, it seems like gravity is strong because it holds us to the earth. But when you compare gravity to electrostatic force of the same object, and it's inherent, right? It's the inherent charge, the inherent charge, and the intrinsic inherent mass of the proton. Well, you see that the force, the electrostatic force, when you go down, is and look at the other calculation, 2.3 times 10 to the negative 18. Now that's still pretty light compared to my weight, but when you compare 10 to the negative 18 to 10 to the negative 47, I mean, that's incredible. That means that, and remember, in the hierarchy, it was gravity, then electrostatic or electromagnetic, and then and now electrostatic technically is different than electromagnetic, but same ballpark. And then weak force and strong force. But 10 to the negative 18 versus 10 to the negative 47, that's almost unimaginably negligible. Like it wouldn't even register. I don't even know how to compare it other than just say it. That's almost 30,000 thousandth of the difference. So 30,000. So basically, electrostatic force is approximately close to 30,000 times stronger than gravity. And it's just weird. Like, there's some paradox there that the weaker the force, the more it looks like it governs everything. Like when you look out in the world, like you know, and the universe, the galaxies, all that's really determined more so we think, it seems obvious, by gravity than any of the other forces, because of order of magnitude of where these forces are, the range of influence of these forces. Electrostatic, magnetostatic, strong and weak, they're more so on the level of the atomic structure, whereas gravity operates on a larger macroscopic scale and has control there. So the as you scale out, gravity has control. As you scale in, these other forces, the electromagnetic, magnetic, and then strong and weak, seem to be the governing forces of the universe. So these are the kind of global things you think about, kind of when you start.